Hi, everybody, and welcome. My name is Elliot Williams. I've been, like the introduction said, programming with microcontrollers, and in particular with the AVR, since way before there was an Arduino. That said, I'm really stoked to see how many people have picked it up in the intervening time. And I've also used to be at HackDC and have seen a bunch of people run into kind of the limits of the Arduino, and maybe you just want to know a little bit more about how the chip works, and learning to program them in C is your introduction if you want to dig a little bit deeper. That said, there's a bunch of hurdles you'll find when you try to switch over from Arduino to straight C. And so this talk is basically an attempt to smooth that over for you guys. So quick outline, I'll do an overview of the chip and how it works. A lot of this will be similarities to how it works with Arduino, and then a bunch of differences. I'll talk about the AVR programming toolchain from compiler through hardware programmer to the chip on a breadboard. This will bring us to making better use of a lot of the AVR's onboard peripherals. And unfortunately, because the peripherals are so flexible, this will end up with a lot of configuration. And finally, I'll deal with some idiomatic C for microcontrollers, in particular how it can make this configuration overhead a little bit easier, and then a quick wrap-up. So I also have far too many slides, so without further ado, the things that will look familiar to you today are if you come from an Arduino background, is the idea of controlling external devices by connecting them to pins on the microcontroller, and you're used to plugging things in. Other things that will seem familiar, you're able to communicate between the AVR and your laptop or desktop computer using a serial port. And then if you need to output analog-like values, you'll use pulse width modulation, which is what the Arduino's analog write is doing in the background. And you'll be able to read in analog values using the analog to digital converter, which is what the Arduino's analog read is doing in the background. Other things that will look familiar to you are the kind of initialization of the chip and then entering into an event loop that repeats forever. In the Arduino, it's usually a setup and then a loop command. We'll see how that goes in C too. So a lot of things you know already will be applicable to learning to program the AVR directly. The things that are going to be new are a different tool chain to program the chip. Instead of the built-in USB serial, we'll have to actually use a physical intermediary. I'll show you how to turn your Arduino into that physical hardware programmer. Other things we'll need to learn is a couple microcontroller C programming idioms that make your life easier, and this is going to be under the bigger rubric of kind of bit twiddling. It's not glamorous, but it gets the job done and as easily as possible. And finally, I'll give you a couple hints about how to deal with the hardware and learn to make it your own. Configuring, eventually you will figure out on your own how to master the internal hardware peripherals. So that's kind of the overview. First question you might be asking yourself is C? Isn't C kind of an old language? Isn't it a dinosaur? And the answer is yes. It's not a modern programming language. It was built for running mainframes back in the old day when mainframes were just about as powerful as the AVR microcontrollers are. Wait a minute. C is a beautiful blend of kind of low-level stuff that we'll need for microcontroller programming without being as horrible and difficult to program as assembler is. So it takes a bit of the memory management burden off you, but still gives you this kind of low-level raw access. That said, everything you know about C is true. It gives you enough rope to hang yourself, but lets you do some pretty amazing, flexible stuff. Other reasons to learn C for a microcontroller include your code will speed way up if you're used to doing it with Arduino code. The Arduino does a lot of things to make your life easier and simpler, and some of them are just inefficient. Digital write takes 40-something cycles in the Arduino because it looks up the registers. If you run it directly, it takes 1, so that's approximately a 40 times speed up if all you're doing is flipping pins back and forth. You'll be doing more stuff like math, and that will make the C comparison not quite as drastic as a 40 times speed up. But your code will run a lot better if you write it yourself and pay attention to it. It's harder to do. There's a trade-off. You're going to have a lot more flexibility if you're coding directly yourself in C. In particular, you can make the hardware peripherals do what you want and when you want them to. You'll have much more fine-grained flexibility in configuring them. And this is what drives most people, I think, who are using Arduino to learn some C finally, is either the speed or the flexibility. Another is responsiveness. Using the interrupt system well and being very careful about offloading whatever you can to the onboard hardware can make your programs seem to run a lot faster even if they actually don't and respond instantly. Finally, a couple advantages of C particularly. I think C is probably available for every CPU known to man. There are probably some that it's not for. I've not had the luck to encounter any of these processors for which there isn't a C compiler myself. And that goes from mainframes down to the smallest microcontrollers you can imagine. More fine-grained, this portability, your code will work on any of the AVR lines. And this is what's more practical for me. I'll often prototype things on the bigger chips, on the mega chips, until I know what's going on, where I have more serial debugging. I have more pinouts if I need them. But then once I find a design is able to switch down to a smaller chip, I'll just copy the code across. And you have to switch some pins around because they're configured differently. But by and large, if you write the code to work on one member of the AVR family, it'll work on another. And things are broadly comparable across brand lines too. If you know how to write AVR microcontroller C, you'll know how to do it for the MSP 430 or other, the PIC line of processors. No problem. So C is kind of an investment in your future. And finally, you just might want to learn about microcontrollers. And C gives you this low-level grip on things that will help you learn more about the internals. So without further ado, let's get into the tool chain. Preface this with my big overview of microcontrollers. What is a microcontroller? They're basically a whole computer on a chip. I mean, you've got programming languages you can compile for it. You've got a CPU that runs, depending on the chip, between 1 megahertz and 20 megahertz, basically for ours. But, a real CPU, it can do math and stuff. You've got a bunch of dynamic memory. This is normal old RAM. And then you've got some non-volatile memory. It stores programs in flash, ROM, and then there's a tiny little bit of EEPROM, which you can think of as storage that will be around when the power goes out, kind of like with a hard drive. So, and then you've got all the other peripherals. It's a whole computer system on a tiny little chip. The problem is, and where this is different from writing for your desktop, is it's a very little computer. It speaks natively 8-bit words, so 32-bit's old and busted. 64-bit is the current standard. These things speak in 8-bit words. Does this mean you can't do 16-bit, 32-bit math? Not at all. It just means it takes more time to do it. You don't have much memory. The AVR chips are graded by basically how much program space they have. So an ATTiny 85 has 8K of program memory. 8K, not much. And they have kind of correspondingly little RAM. So your programs are going to be tight. There's no operating system backing you up, and this means you're going to have to do low-level input and output. You're not worrying about files and writing to monitors. You're worried about flipping pins. And this leaves you with this position where you're kind of halfway between being a component and a computer when you write for this. And that's where C is pretty much a decent language. What can you do with all this? Well, you've seen it all. I will skip through this slide pretty quick. You can make fancy blinkers, persistent vision toys, robots, quadcopters, 3D printers run basically on AVR chips written in C. The RepRap claims to run Arduino, but really underneath it's mostly C with a couple header files. You can make data loggers, GPS, energy monitors. You can log your power over time. You can make your own USB devices, et cetera, et cetera. Basically anything where you're thinking about the interface between the real world and the computer world, this is where your microcontroller wants to be sitting as the glue logic. How do we do this? It turns out the answer is really stupid. It's all about flipping voltages on pins. And it's going to be either input or output largely. Output, really all you're doing is applying a high voltage or a low voltage, say 0 volts or 5 volts, to any pin. This sounds really limited. You've got a chip with 28 pins. You can use probably 23 of them and put voltages out on them. But with this, you can actually turn LEDs on, you can flip switches, you can spin motors. So it gives you a lot of real-world control all of a sudden. And then if you do it, if you flip these pins in time, you can make serial communications of all different sorts. You can talk to other chips or your computer, or over UART serial to your computer through SPI or I2C to other chips, USB to your computer again. So flipping digital output pins high or low is actually remarkably powerful. But if you want analog out of it, like you want to dim an LED, you can use pulse width modulation. And this is what Arduino's analog write does. If you've been in denial enough that you think it's actually spitting out analog values, what it's really doing under the hood is flipping the digital output pin on and off super quickly, and the fraction of time it spends high and low determines the average voltage value on this pin. So you're still talking all digital output, but the things you can do with this, have brought us the modern computer era, right? So it's not a super limit. On the input side, what we're going to be doing is reading voltage levels applied to the pins. Most of them are digital inputs, so is it above or below halfway between 0 and 5 volts? But this lets you detect whether a push button's been pushed or receive digital communication. There are also on this chip analog to digital converters, which let you read real-world continuous voltages like light levels or audio waveforms or et cetera. The input pins have 2 pin modes. This is all going to be familiar to you Arduino folks, right? They have high Z mode, high impedance mode, which is effectively disconnected from the circuit, where it just reads the voltage on the line without influencing it. And then it has an internal pull-up resistor, which can be attached that pulls the voltage high. So you can test if anything is connecting the pin to ground. So that's great for testing push buttons. And this is all normal configuration stuff. You Arduino guys have seen all of this before. If you had to handle all this yourself, you would be going crazy. If it were not for the chip's internal peripherals, all of the stuff about serial ports would be absolutely impossible. You would spend all of your CPU time just trying to get the serial read and write timing correct and wouldn't have any time for doing math. So imagine the situation where you've built a robot and it has a bunch of tasks it needs to do. And it needs to, for instance, monitor the serial line. Maybe you're going to type commands to it. It needs to control a couple motors and their speed even. So it's doing PWM on 2 motor lines. It needs to blink some LEDs because robots blink LEDs. And it needs to be ready to turn off its killer laser as soon as it hits a bump switch. If you had to write the code to do all this, even if you could test all those input and output lines, et cetera, it would bog the CPU horribly down. On the other hand, if you can offload all of these tasks to the onboard hardware on the chip, then your CPU is sitting there idle and just coordinating among them. And this is the right strategy to approach microcontroller projects, in my opinion. Monitoring the serial line, that's the serial hardware peripherals job. Controlling the motor speed, that's the PWM peripherals job. Blinking LEDs, yeah, we can hand that off to the timer counters again. Looking for a button to be pressed for maybe bumping into somebody, that's a job for the interrupt system. The point is there's all these onboard hardware peripherals which can do all of these things for you. And so it'll seem to your CPU and your code like it's doing all of these at once. And that's really why you would want to learn to write C for these things, is that controlling all the peripherals simultaneously and making them all work together is really kind of the heart and soul of microcontroller programming, and it's a long road to get there. The chips we'll be working with in particular look like this. I was talking about inputs and outputs and peripherals. So here's the pins. Just quick orientation, the AVRs are laid out in banks. So some of them are in B, some of them are in C, and some of them are in D, and I have them color-coded green, blue, and yellow here. They're scattered all around the chip, which is one of the things I like least about the AVRs. And in parentheses, so I've written their pin names as they're listed in the data sheet next to the pins, so PB1, PB0, and then in parentheses their main functions. And so that's where the internal hardware peripherals are hooked up. And so you can see things like in the upper left-hand corner, pins 2 and 3 are PD0 and PD1, but they're also used as the serial receive and transmit lines, respectively. We'll talk a lot more about this as we go along. Notice that not every pin can do everything, and a bunch of the pins have multiple functions. So, for instance, in the top right, you have a pin PC5 that has both analog to digital converter number 5 on it and the serial clock for the I2C line. So you're going to have to make some choices as to what you want the chip to do and personalize it. And this is where I come to my quick Arduino rant. Arduino is a fantastic development kit. It's got all the parts you could possibly need on it. And a lot of the time it has more than you need. Maybe you don't need the chip to run at 16 megahertz. Maybe you're making a low power design. Maybe you don't need the USB to serial converter. It's all extra stuff on the chip. The Arduino language is very simple to learn, but because it's simple, it hides some of the flexibility of the chips from you. And so, for instance, sometimes you can't do things you'd like to without drastically overhauling it. A friend of mine, Ash, used to say working with the Arduino is like knitting in boxing gloves. I understand what he means. He's a assembly programmer for embedded networking devices, so he's kind of a wizard. But his basic point is that sometimes doing things that would be simple if you understood the hardware are not simple with the Arduino because it kind of obscures that from you. And I used to be an economist. My take on the whole thing is that these companies, Atmel and et cetera, have survived over the last 40 years by making microcontrollers to do what you want them to do. Companies' fortunes rise and fall on whether it's got the right peripherals internally to sell to some engineer that he will use the chip in a design. These guys have been trying to make this chip do what you want to do. All that's left for you to do is learn what it does. So, without further ado, we'll step into the tool chain. The life cycle of writing for the AVR is a lot like it is for the Arduino. You write code, you compile the code for the AVR machine code, you transfer it over, except instead of with the Arduino, where we're transferring it over using a USB cord and a USB to serial adapter that's built on, we're going to need something in between. And the AVR chips want to be programmed using the SPI protocol. And so what you need basically is something in between your laptop and the AVR chip on your breadboard that speaks the SPI protocol. And this is what I'm going to call a hardware programmer. And so this is something that translates to the AVR chip. On your computer side, on your laptop side, you're going to need software to run this programmer. So software to speak to the programmer, and then programmer to speak to the AVR in SPI to get it programmed. Once you program it over, you get feedback and debug until it works, just like usual. The first step there was the cross-compiler. In this case, we'll use the GNU AVR GCC cross-compiler, which is actually the same one as used for Arduino under the hood. So that's not actually any different. For a hardware programmer, I'll give you a bunch of options later, including turning your Arduino into one. So we'll handle that in a second. On the laptop side, the standard these days, everybody's using AVR Dude, which knows how to talk to a wide variety of hardware programmers, from your Arduino being used as one to 5 wires hooked up to a parallel port. So if you have a hardware programmer, chances are good AVR Dude knows how to speak to it. One thing that's idiosyncratic about C, I think, is that it's not really full freestanding language. You need kind of a lot of stuff to compile for it, and this is where makefiles come in. A makefile basically keeps track of all your particular setup and runs all of the right command lines, links in different batches of source files, et cetera, et cetera. It does all the kind of grunt work to compiling a C program for your AVR for you. So you're going to find a makefile, and that's going to be new to the Arduino stuff, although Arduino has its own makefile that's just not exposed to you. You'll be able to find it, actually, if you look for it. Finally, and this is something you might want to go out and buy, is a USB to serial converter cable, a freestanding one. I use this all the time, every day. If you're serious about doing any kind of embedded development, you can always get serial data out, so it's a fantastically useful thing for feedback during debugging. Let's see. In terms of the software, downloading the software part of the tool chain is free and easy for basically everyone. Linux, if you're on a Ubuntu/Debian-like system, here's your command line. I think for Red Hat, it's AVR GCC instead of GCC AVR. The rest of you Linux guys will know what you're doing. For Windows, there's an old package called WinAVR, which is about, I think the last update was 2010. It's actually completely workable as such. Atmel, the company that makes the AVRs, also has its integrated development environment, AVR Studio, which a lot of people recommend. They also secretly put out a new and constantly updated compiler tool chain that doesn't use the integrated environment, but you have to root around for that. You can't lose with either WinAVR or AVR Studio, depending on whether you want to type make yourself in the case of WinAVR or use an integrated development environment and press a button in terms of AVR Studio. For Mac people, there's software. It's basically the same tool chain under the name CrossPack, put out by the people who make my favorite USB library. And if you're into the integrated development environment, Xcode's supposed to be fantastic, right? So that gets you set up with the compilation software and the front end, the software end of your tool chain. Now we need to think about some hardware. So like I said, AVR uses this SPI interface. Oops, that's redundant. It's serial parallel interface for in-system programming, which is acronym SALAD. And basically this consists of hooking up 4 pins plus power and ground to get to the AVR to talk to a programmer. And these are the 3 of them are the normal SPI lines, signal clock, serial clock, master in, and master out, and then the reset button is used to tell the AVR that it should expect data coming in. And then the other 2 lines are power and ground. So the bottom line is 6 wires hooking up to the AVR to program it, and then something in between to talk to it. Here this graph just outlines which pins they are. If you're looking at the AVR plugged into a breadboard, the pins in color on the chip are the ones you need to hook up. If you have an already built SPI programmer, there are labels on the other side, and you can just connect yellow to yellow and green to green, and you're set to go. Otherwise, this is just to tell you that you've got 6 pins you need to hook up. If you'd like to take off and try this with an Arduino as your hardware programmer, maybe you've got one sitting around, plug an AVR chip into your breadboard, plug your Arduino up to your serial or up to your USB port. You can flash this program in. It's called Arduino ISP in System Programmer. It's in Files, Examples menu. Flash that into your Arduino, and then you're set. Your Arduino is an AVR programmer. All you have to do is hook up the wires. Here's a command using AVR Dude, the program that runs the programmer on your laptop, that'll test if everything's hooked up right. You're going to hook it up as in the next slide. If that works, you'll see a bunch of details about the chip. If it doesn't work, try again until it does. Here's how you would wire up your Arduino for ISP. This is the super fancy version. I've included 3 LEDs. One is ready to run, one is running, and one is there's been an error. Those are entirely optional. The lines you can see that you need are power and ground, which are red and black respectively, and you can see I've run them out to the power rails and then jumpered them over to the AVR. The blue wire is the one that runs to reset. Green runs to system clock, and then gray and orange run to master out and master in respectively. So those 6 are the lines you really need if you'd like to program the chip. The LEDs are just bling. At this point, you've flashed in Arduino ISP into your Arduino. You've hooked these up to your target AVR on the board. You're ready to go. In reality, it'll look a little something like this. Here it is on my breadboard with a bunch of lines hooked up. This is not super special, but I promise you it works. If you get tired of using your Arduino as your in-system programmer, like you want to use it for Arduino prototyping again, you can make your own permanent do-it-yourself in-system programmer pretty easily. A package I recommend is VUSBTiny, which is a super minimal design. It uses 1 chip and a couple Zener diodes and some resistors, and that's it. It speaks USB and then transfers that over to the chip to program it. That's fantastic. There are more professional DIY projects that are a little more involved, use an oscillator chip and et cetera for precise timing. I recommend both of these. I've built both of them. And you can, if you're feeling really ghetto, you can just hook up wires to a parallel port. Of course, this means you have to have a computer with a parallel port. If you want to buy something and spend some money, which is not a bad way to go necessarily, Atmel's programmer, the AVR ISP Mark II, is really good. It's a very robust programmer, speaks to all of the different AVR chips, but it's about $40, which isn't super much money. If you want to solder something together yourself, the usual hobby places have USBTiny kits. If you have a bus pirate kicking around, you can use that in SPI mode to program your chips. And finally, there's a bunch of, I should say this in good conscience, there's a bunch of really cheap knockoffs of the USB ASP design, mostly from China. Some of these are a little bit electrically fragile in the sense that they have power limiting resistors on their outputs that make the digital logic voltage, especially if you're using long cables, which they do for some reason, a little bit sketchy. And you can remove these resistors, but then at that point, you know, you might as well make yourself a solid DIY design or pay $20 and get something a little better, in my opinion. On the other hand, they work. Here's a family portrait of all these. Here's an Arduino hooked up as an SPI, number 1. Around the corner is an old Lady Ada USB Tiny kit. Number 3 is one of those Chinese programmers. Number 4 is a sweet little surface mount USB Tiny from a German manufacturer. And number 5 is something I'll show you in another couple slides again, which is those same 6 wires, but in the shape they are on the chip, broken out, so you don't have to wire it up every time. I recommend this highly. Again, it's something for you to do or buy. This is for your reference. If you've bought an ISP, it'll have a 6-pin header. This is how you hook the pins up to your AVR to program it. Again, it's the same as it was with the Arduino, power lines, the blue to reset, and then the others to the regular old SPI pins. Have a look at the slide later when you need to hook it up. That's what it looks like on the breadboard. You can see this is a little bit of a dodgy arrangement with those 6 pin headers stuck into the cable. Here's what I use every day, something a little bit more refined. Again, this is this little programming spider that just fits right down over the chip and connects those 6 lines up for you. All in one little breadboard. Sweet. I even labeled the pins on it. It's totally handy. You should make something like this for yourself. I have plans for mine up on my GitHub if you are able to make circuit boards or just want to do it yourself. So you've got the compiler, you've got a hardware programmer. Now it's time to set up your makefile so that it knows what your target chip is, what your programmer is, and other options if you need it. Editing makefiles is no fun, but just make sure that you're opening the makefile that's in the same directory as the rest of your project, like where your code is, etc., and then edit it so that it knows what kind of AVR chip you're targeting and what programmer you're using, plus any of the other options for AVR Dude. I'll show you how to test those on the next slide. And once you've done that, once you've edited the makefile, you open up a terminal window in the project directory and you type in make flash or make program, and it's done. This is what happens when you press the little play button in the Arduino IDE, is it runs in the background a makefile that compiles the program for you and then sends it across to the chip. And if you're successful, you get, in our case, in the code I'll show you in a few slides, you get a blinky light. So here it is on, and here it is off. And if this were live video, you'd see it switching between these two back and forth about once a second. I'll show you how that code goes in a sec. Just to be sure you really know what's going on, you might want to flash the chip manually. So if you're having trouble with the makefile, take a step back and run AVR Dude by yourself. If you want something to flash in the chip, the first step is to type make, and it'll create the machine code file for you. It'll be a hex file. With some make files, you have to type make hex. If this works successfully, you know there's not a bug in your program. Well, that's not true. You know that your program compiles and is ready to send over the chip. Typing in AVR Dude lines like the following will let you test out the connection then between your chip, between your computer and the chip. So here I'm specifying which chip, which programmer, and then which file. In my case, it's a hex file called blinkled.hex. The line above is for USB Tiny. The line below is for Arduino. Arduino's AVR ISP interface, 19,200 baud over the serial port. People on Windows, that string that reads dev tty acm, that's going to be COM3, COM4, or COM5, something like that, depending on where it's attached. The options you need to know are the chip type, which is under P, the programmer type, which is under C, and then the hex file. Alternately, those serial options I just mentioned before. Finally, I guess I'd just like to say it's good to test this out by hand. And then once you've gotten these arguments to the command line written, you know what exactly to paste into the makefile, and then you'll never have to type them again. So here's the code I typed in. This is AVR C now. It's a lot like Arduino code. You'll see, but some things are different. So at the top we've got include files. These include other code. In this case it's including pin definitions and stuff. C code always starts with main function. That's its point of entry. That's where it all starts. And then from then it looks like Arduino code, right? There's a top section where I do some initializing. We'll talk about what that means in a sec. And then there's a while 1, which is an endless loop. 1 always evaluates as true in C, so while 1 is always true. So this is the equivalent of the loop command in Arduino. This is the loop from which it never enters. And I've written things out in a funny way with binary numbers so that you can see what's happening. We'll talk about this in a few more slides. I'd like to talk first, though, about configuring peripherals, what the peripherals are, what they're good for, and how to configure them briefly. So before we get back to blinking LEDs, let's talk about fancier stuff. The most useful built-in hardware peripheral, I'd say, is the timers. Microcontrollers run too fast to interface with people. People like things, with a little bit of a delay in it. The ATmegas have internal counters that will count up at their fast 8 megahertz speed, but then only do something every time they hit 255 or some higher value. So you can divide down the fast speed into something that works on human speed. And this is the way the millis command works in the background on the Arduino. It's counting up these seconds using the AVR's internal timers to divide it down to something reasonable. You can do really fancy stuff with the timers in terms of scheduling events if you use them to fire interrupts. This can get insane. You can build your own operating system. Timers also make pulse width modulation really easy. You can tie the timer to an output pin so that it turns the pin high and low depending on where the counter timer is. And this is the way the Arduino analog pins work. They flip things up and down. They flip the pin up and down, high voltage, low voltage, automatically using the internal hardware. Interrupts are fantastic. Using interrupts well is what separates a good C programmer from a good microcontroller C programmer. They're triggered by, I think, 20-something different events. And when this event happens, the flow of code goes from whatever it's doing currently to run a subroutine that you've defined as an interrupt service routine. And then once that's done, it goes back to your code. So what this is great for doing is monitoring things. So if you need to monitor the serial line, you set an interrupt to flag when new data comes over serial. If you need to monitor the input pins for button presses, you do the same thing, and then as soon as the button's pressed, the CPU puts down what it's doing, flips over to the interrupt service routine, runs it, and then picks up again where it left off. So these are fantastic. Instead of waiting and looking to see if something happens, using interrupts, you can fire code as soon as whatever that is happens. There's a ton of built-in serial peripherals. We talked about these earlier. There's asynchronous serial SPI, which is good for really fast communications to a small number of devices, and I2C, which is a little slower, but it's kind of got a network flavor to it, so you can address 128 different devices off of that. And all three of these run independently and on their own. So you just kick the data you want to send off to the SPI, and it worries about the details of sending it out for you. Analog to digital converters, we've talked about. That's the analog equivalent of analog read. And then memory chips. all of these hardware things are super versatile, and the good news is that you can use almost all of them simultaneously. There's some overlap, like I mentioned, with the ADC pins and the I2C pins in the upper right-hand corner. All of the hardware PWM pins are labeled OC something something, where OC, the first number is the timer number. So there's 3 timers on this chip. There's 0, 1, and 2. And so they're OC 0 something, OC 1 something. And then there's usually 2 PWM pins per timer. So it's OC 0A, OC 0B, et cetera, et cetera. And so you could see how they're scattered all over the chip, largely not overlapping each other. You're going to hate that the SPI pins are shared between, if you look in the lower right-hand corner, you're going to hate that the SPI pins are shared with 2 of the PWM pins. And, yeah, that's always a choice you have to make. Peripherals are awesome. They do everything for you. They run independently of the CPU. You can trigger interrupts so you don't have to wait for anything. Clever use of these can let you do many, many things at once. They're all very flexible. Arduino hides a lot of this flexibility from you, so you're not used to this, by which I mean they make configuring the chip a lot simpler. The downside of peripherals is that they require all of this configuration. If you want to do input and output, it's easy. You select the pin mode, and then whether it has a pull-up or not. So that's 2 things you have to worry about. But if you want to talk about setting up PWM, you have to set, first of all, a timer. Then you have to set the timer speed. And then you have to put the timer in PWM mode. And then you have to decide whether you want to toggle a pin or not. And then if you wanted to trigger an interrupt instead, maybe you want to make like a ticking clock kind of thing, like milliseconds, you might want it to trigger an interrupt. These are all things you have to configure on the chip. So how are you going to figure out where that all comes from? The answer is the datasheet is your friend, or maybe your frenemy. It's 660 pages long for the Mega Series chips. The datasheet is a beast. It's an encyclopedia, not a novel, and that's how you want to approach it. You don't want to start at the beginning and start reading this thing. It'll kill you dead. In fact, I'd say the first 2 pages are a really good read. Page 1's a summary of all the peripherals and abilities. It tells you, how much power the chip needs, what its maximum voltages are, all the specs. Page 2 is that pinout diagram where it explains all of the functions of all the different pins. You'll be using page 1 and page 2 over and over. I would not read the next chapter. It talks about the CPU. Say you want to implement something using a serial port. At that point, you skip to the chapter on the serial port, and maybe you read the chapter introduction and try to understand the block diagram. You want a basic idea of how the hardware peripheral works. Once you think you've got that, you skip to the end of the chapter where it talks about the configuration registers. And this means if you got the intro, you know basically how the thing works. And if you can figure out which registers you need to flip which bits in to make it do what you want, then you know how to make it do what you want. So in short, first get the broad overview by reading the beginning of the chapter, then flip over the registers. Registers? Yeah, registers. The special function registers are the real secret to configuring everything in these chips, in microcontrollers in general, AVRs in particular. They're called special function registers in the data sheet. They're basically fixed memory locations with side effects. That is to say, you can read and write to them just like a normal variable, so you can say like A equals 1 or port B equals 7. But don't think of them as numbers. Each bit in this byte, there's 8 bits in a byte. You want to think of these as being 8 separate switches lined up, and because they are. And each switch internally in the chip has a special function connected to it. And so these are bits in a byte, but each bit is a memory that has a side effect. And what the side effects are depends on which register, which bit. So for instance, in our blink LED program way up there. Wrote something that seemed cryptic at the time. It was port B equals this number, which is actually 2 in binary. Note that GCC lets you write out binary numbers like this. It's really great when you want to visualize all 8 of those little switches in the registers. That's special to GCC. That's not standard C, but it's really awesome. So here we're flipping the switch that's second over from the right. I'm going to be calling that the switch that corresponds to pin 1. And so when you set this, so it looks like we're just writing a number to a variable. But because this variable is a special function register, what it's really doing is it's writing this number to the variable, but when that second bit in the number is set, there's a little transistor connected, and it turns on the pin that we want it to turn on. In this case, it's going to be PB1, and our LED lights up. So this is how everything works in the chip, basically. You have these special function registers. You write a numeric value to them. This value sets up the bits in that register in exactly the right way to flip the switches that you want flipped. And those switches being flipped control the chip. And so that's the secret sauce to how everything in the AVR works. Let's talk a little bit about hardware configuration then. I'll work through 2 simple examples. You don't usually think of input and output being hardware peripherals, but they are. You know this from Arduino, right? You call pin mode before you want to read or write to a pin, right? You have to tell it whether you want it to be in write mode or read mode and whether you want the pull-up on. We're doing exactly the same thing here, except we do it with the data direction register. And if you look in the data sheet, that's what this thing is called. It's called the data direction register, and there's one for port B, which has 8 pins. There's one for port C, which has 7. That's kind of weird. And there's one for port D, which has 8. And each pin out on the chip corresponds to a bit inside these bytes in the data direction register. And you turn them on for input or output depending on whether there's a 1 or a 0 in that bit. So code like this, data direction register B equals blah, 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 with a 1 in the PB1 slot, sets the port into output mode, for instance. If there were a 0 there, it would be left in input mode. Yeah, I think you've noticed by now that AVR hardware and C all starts counting at 0. So the rightmost bit is the 0 bit, and then the one after that is the 1 bit, etc. So PB0 is on the rightmost bit, and PB1 is next to that. Anyway, the point is, everything the chip does is configured by setting and clearing bits in registers. Give you an example of how this can get crappy pretty quick. Let's say we're setting up PWM, and so we want to set up something kind of Arduino-like. We want to have analog out on pin B1. We need to configure 3 things: timer clock source, we need to set the PWM into PWM mode, and then we need to enable automatic output on that pin. I'll show you how this looks in the data sheet. Oh, I hope you can see this. At the top is the timer counter control register. And you can see that there's 8 slots there labeled 0 to 7. And they're all read and write. And they all have a bunch of kind of quasi-mnemonic names like WGM10, which is waveform generation mode 1 for counter 1, and it's the 0th bit. And then you look down at this table that's a couple pages down in the data sheet, and it tells you how setting all of these different bits sets it into different modes. So say we want to set it into fast PWM mode. And so you look down at which bits you need to set, you set those bits, and you are good to go. The other bit we're going to need to set, and I know this because it's even further in the data sheet, is one of these COM bits. So bear that in mind as we go through. Now imagine you're doing this. We need to set these waveform generation bits. 2 of them were the low bits in this register. And so if you know your binary math, the lowest one is worth 1, and the next one over is worth 2, so 1 plus 2 is 3. So we could set it to 3, and that would take care of the waveform bits. But now we need to also set this COM bit, and you look it up in the chart again, and it's bit 6. And you're like, bit 6, what's 6 in binary? Ah, Jesus, it's 64, plus 3 from before is 67. This is horrible. And even more to the point, if you just write this register equals 67, you're not going to be able to tell how it's configured later when you go to read that code. There has to be a better way, and of course there is. And this brings us to writing idiomatic C for microcontrollers. And I'll show you the secret right about here that lets you translate from the data sheet directly into C code. And unfortunately, it's about binary logic. That said, I'm going to gloss through some of it, and I'll show you my favorite macro tricks to deal with it without having to think hard at the end. The next couple slides are going to go by a little quick. If you're not caught up on your binary logic, you may have to scratch your head about them later on. So a lot of what we're doing here is really low level, right? We're flipping bits. If you've programmed C, and I've written in C since way back, 1990, it's not like writing for big computers when you write for microcontrollers. We're going to be trying to get one bit in one register flipped instead of creating, big elaborate structures that encapsulate our data well, et cetera, et cetera. So we're going to be using some operations maybe you're not even used to. That is the bitwise logic operations, bit shifts, bitwise and or, et cetera, to flip bits. And this I call basically bit twiddling. It's a little annoying. You get used to it. It turns out to be totally everyday life. And I wouldn't run through this if you didn't need it. The problem is everyone else's C code is going to be written using these bit shifts and bit masks and using bitwise or to set bits and et cetera. So you're going to need to be able to read it, even if I show you a way to cheat out at the end with some elegant macros that makes your code more readable. So here goes. Dive in. Thinking caps on for a sec. So here is our blinking LED code again, and have a look at the DDRB equals something line. Remember that what we're doing is we're putting pin PB1 into the on state, so we're enabling it for output. So we're writing a 1 into the data direction register. And then down in the main loop, we're turning that bit on and off in the port B, which is the one that controls whether it's lighting the LED up or not. The way I would write this, or at least a little closer to the way I would write this, is the following. Imagine that I'm going to flip back. Imagine that you wanted to change this code to work with a different pin. Maybe you switch to you put your LED on PB0 or PB3 for all I care. You have to change all of these numerical values everywhere that this occurs in your code, and that's lousy. So the first thing you want to do is use some defines to abstract away from where the LED actually is. So I always do this when I write new AVR code. You should too. It's like a hardware abstraction layer, but real small. Define LED as PB1 up at the top of those define lines there. Tells you that you've hooked your LED to PB1, which is awesome. Now you know how the schematic should look, but it also means that from now on you can use LED wherever you want to talk about what you're doing to the LED, and it instantly makes your code more readable. And then the rest of it is these funny bit shifts. And if you've done this before, you can close your eyes for the next 5 minutes, and if this looks weird to you, I'm going to explain it to you in the next 5 minutes. What's going on with these bit shifting? So I'm taking the number 1, which is 1 in binary. There should be an extra 0 in here. Sorry about that. Should be 7 zeros and a 1 at the end. That's what 1 looks like in binary. The bit shift operator, in particular the left bit shift operator, is these 2 less than arrows. And when we shifted 1, which is a 1 in the least significant bit, over by 0 bits, you get 1 again. If you shift it over by 1, you get the binary number 2, but more importantly, you get a 1 in the number 1 slot. If you shift it over by 2, you get a 1 in the number 2 slot. Note that's the third one if you're counting like a human, but it's the number 2 slot if you're counting like C. Same thing for 3, 4, etc. So what this lets us do is it lets us refer to the bit number that we want a 1 in by just putting a 3 down. So we want a 1 in position number 3. We write 1, bit shifted over 3 times. This is awesome. How does something like where we refer to it by the pin name work? So up in the top, I was suggesting we could take PB1, or we take a 1 and we shift it over PB1 times. How does that work? Well, it turns out all of these pin names are defined for you in this io.h file that we included at the top of the code. And it turns out that every pin, every register, and every option you can set for every configuration is defined as a macro in this io.h register. This means that you could take stuff that comes straight out of the data sheet, type it in using these bit shifts, and it sets the right bits in your code. It's actually fantastically convenient. So say we wanted to turn on a couple bits, a couple LEDs, right? We've got LEDs on pins PB1, PB7. What do? We can use the bitwise OR. You make a PB1, so you shift it over to PB1, which in this case is a 1 shifted over once. You make a PB7, which is a 1 shifted over 7 times, and you OR them together. And if you look down the columns, this is a bitwise OR operation. That is to say, the result is a 1 whenever either of the two above it, either or, are a 1, and a 0 when otherwise. Right? So this is a great way of making a bit mask with 2 bits set. Applies logical OR down the columns. Imagine you want to toggle a bit. It turns out that XOR is really good for this. XOR is 1 if and only if the 2 bits it's comparing are different from each other. That is to say, if 1 is 1 and the other is 0, or if 1 is 0 and the other one's 1, the result is 1. If either of them match, if both are 1 or both are 0, the result is 0. And so this means you could take something like this. Say I have the 4 bottom LEDs lit, right? That's 0, 0, 0, 1, 1, 1, 1. And I want to turn one of them off. I want to turn off the PB1, the PB1 1. I can XOR it with this number. All the ones that are on stay on because 1 XOR 0 is 1. All the ones that are off stay off. And then the one that I selected gets flipped. Awesome. You're going to have to work through the bitwise logic yourself for the others. I'll show you how this is all used in a summary in a few. Not is fantastically easy and fantastically useful. It takes all the bits that were on, turns them off. It's great for making blinking patterns, but its real use is for clearing bits. And this is the way that goes. It ends up using bitwise and not to clear a bit, which sucks. This sucks a little bit to get your head around. Here goes. And is 1 if both bits are 1. So the result is a 1 if input 1 is 1 and input 2 is 1. Otherwise, it's a 0. This makes it totally useful for zeroing things out. So if you start out with 4 bits off, 4 bits on, and you AND it with something that has only 1 bit off, then you clear out that 1 bit that was off. The easiest way to make a string with all bits on except for 1 that's off is, ironically, to make the opposite of that string and then not it. So in our case, we want a string with a 0 only in position PB1. So we do the 1 shifted over to PB1 trick, which gets us a 1 in that spot, and then we not it, which gives us the inverse of that, which is only a 0 only in the PB1 slot. And then we're ready to AND it with the original value and 0 it out. So this is how you clear a bit. And if These you just have to go over a couple times in your head. So if you want to turn off the bit without touching, if you want to turn off the bit corresponding to PB1 without touching any of the other ones, what you do is you say port B equals port B and the negation, the not of our bit shifted over. And so what that's doing is it's taking whatever was in port B, zeroing out that one bit, and then writing it back into port B. And this is, again, the way the registers look like regular variables. And then the shorthand for this, of course, is something equals something and something can be shorthanded to and equals. And this is what you're going to see. This bottom line is what you're going to see in the majority of everyone's code when you look at C. So this was horrible. This is bitwise logic, bit twiddling. And I'm going to give you the summary real quick so that you can see all three of them together. If you want to set a bit, you use OR and a bit shift. If you want to toggle a bit, you use XOR and a bit shift. And if you want to clear a bit, you use and then a knotted bit shift. That is a negated bit shift. Man, these are painful. You will see this in everybody's code. The trick is, after you do it for long enough, you will start to read them for what they really are. Oh yeah, here I'm setting bit PB1 in port B. Oh, here I'm clearing PB1 in port B, etc., etc. There was a point to all this, and that is that we had all of these bit names from the data sheet. Remember, we wanted to configure things by setting and clearing bits in control registers, and they had these nice mnemonic names for us. So for instance, if we want to turn a pin on for output, we can write a 1 to its bit in the data direction register, and this is the idiomatic way to do that. It's the control register or equaled with the bit shifted over. This lets us refer to the bits by name. This is totally useful when you want to set something in a control register where you've got 6 bits that you want to set on, and they all have these crazy names, and I'm just reading these names out of the data sheet. I don't want to look up which bit it's in. The compiler handles that for you. So you OR them all together, bit shifted over, and then you can write them to the register. Similarly, if you want to turn a bit off in a register without clobbering any of the other bits, so maybe we want to turn off the pin flipping output on the PWM without changing the PWM mode or any of the other setup for that peripheral, you can use this and with a knotted bit shift to flip off just that one bit. And you'll see this all the time, and this is easily the strangest thing to you if you come from Arduino land. You'll get used to it. If you don't want to get used to it, here is 4 macros that can do all the bit twiddling for you. The first one just does a bit shift. The mnemonic is bit value. The others set, clear, and toggle bits just as we've described, using the same thing. And these macros work in standard C, and to my eyes make the code a lot more readable. You'll see it written both ways, so you'll have to learn to read it the other way, even if you always write it using these macros. And frankly, I do one or the other depending on the phase of the moon or my mood at the time. Here's the way I'd write blink LED. But you can see how this doesn't work if it's the first time you've ever seen this code. So at the top, I define my pins. Oops, I did PB0 there. Maybe I changed the LED over to a different pin. You define the pin and then its configuration registers. Then I define those 4 macros, and then I just use it. And this simplifies your code a lot. Now my init section reads set bit LED DDR LED, right? So I know I'm setting the bit for the LED in the data direction register. Similarly, in the event loop, I shortened it even more so it would fit on the slide and just use toggle bit instead, because I'm just blinking this thing on and off. Again, it's really unambiguous when you're reading through this what you're doing. And so I hope this bit was a little bit helpful. The summary is you go from the bit name definitions in the data sheet through these bit operations straight to configuring it in your code. And once you get used to that flow, it's actually really easy. It's just looking it up a lot. So we've covered a lot of ground, probably too much, for which apologies. I hope your brains are still intact. The AVR GCC programming toolchain. It's a lot like what you're used to for Arduino, except now we've got a hardware programmer and some breadboarding in the middle. I covered this kind of million-mile-high overview of the peripherals and why they matter. That is, anytime you do something that involves blinking, see if you can do it with the timers and an automatic pin. Anytime you do anything that involves input or output, you hand that off to the serial registers. Anytime you need to respond to something instantly, you can do it with the interrupts. ADC, analog to digital conversion, there's no other way around that, so you're always doing it. These are all ways of sharing your scarce CPU time to make things work. Finally, we went through kind of rudimentary bit twiddling and how it works on the configuration registers. And this should show you this kind of overall view of I need to figure out what the things do, so I read it up in the data sheet. I've got these mnemonics. How do I turn those into my code? Oh, with bit shifts. And in truth, this is all of the hard stuff of moving from Arduino-style code to C-style code. I covered it in one brain-numbing hour, but this is it. And so when you do digital write next time, think about those 45 cycles that it's taking to do it, and think to yourself, yeah, you know, maybe I could just write port B equals something, something. And heck, if I even wrote a macro, I could do it, you know, and so it would be readable. And then it would go in one cycle. So I could toggle that pin 40-something times faster. Yeah, if that doesn't inspire you, I don't know what will. What's left for you? Oh, good Lord, lots. I haven't covered any of the specifics of any of the peripherals or how they work or what they're good for. I actually go through, I just finished up this book. I go through probably 10 chapters, working one chapter per peripheral, and I push them really to their limits. The timers can count so fast that you can make an AM radio by toggling one of the pins on and off and then modulating sound over that. You can play back sampled audio by running these things fast enough. This is all stuff that you can do only if you have access to the configuration registers and know how to use them. So there's a lot of, you could push these peripherals to their limit, and I personally think it's super fun to do that once you know how they work. Setting up event priorities with interrupts is phenomenally useful, and setting up things like a system clock with the timers is great fun. There's all sorts of other functions on this chip. There's a watchdog timer that resets the chip automatically if it hasn't seen an I'm okay every once in a while that prevents you from ever locking it up. There's sleep modes that make it use microamps of power when it's in the sleep mode. And there's a special one that shuts the CPU down so that it doesn't make digital jitter so that it can get a nice clean read on the analog to digital converter. The chip's crazy. It's got a ton of functions, and it would take 10 of these seminars to cover them all. So that's for another time. The data sheet is your friend. Dig in. There's tons of examples out there in the world, too. So with that in mind, here's some resources. I'm slowly populating stuff on my website that ostensibly supports the book, but I'm really just trying to find an outlet for putting up all of the little fun hacks that I've done with AVRs, from my coffee roaster to AVR to USB gadgets to et cetera, et cetera. So I'm posting those up as we go along. At my website, I've taught AVR classes at HackDC, my old hackerspace. There's good resources up there, including more detailed slides that cover all similar material, and then some code and boards and et cetera. If you want to get really serious about C, I really like this guy, Bruce Land at Cornell University, has an engineering course on using AVRs with C. He's also put his lectures up in YouTube. They're a really great watch. they're aimed at engineers, so it's a little highfalutin, but he's right on all accounts, and I think they're actually pretty accessible if you're really ready to take that next step. If you're just feeling like hobbying around, which is what I do most of the time, there's Hackaday, MakeBlog, SparkFun, Lady Ada, all of the usual places for inspiration for projects, and plenty of code examples. If you're interested in USB stuff or building your own SPI programmer, I'm a big fan of the VUSB library for USB stuff, and the VUSB Tiny Programmer in particular. Give that a look. And I'll try to answer some questions real quick and then wrap up because I am over time. Let's see. Questions include power requirements for this class of chips. That's an awesome question. The truth is it depends on what speed you're running the CPU, how much computation you're doing, whether you're running the analog to digital converter, etc. There's a whole chapter of the datasheet on power reduction. You can get them to run, if you're not doing anything, in standby mode, maybe waiting for something to come in over the interrupt serial or waiting for somebody to press a button, on a few microamps, maybe let's say 8. So, less than a battery's internal discharge. While they're running and doing serious number crunching, it can be 20 or 50 milliamps easily. It's less than the bunch of LEDs that you're driving with it, but that's a good amount of current. You can actually drain batteries at 50 milliamps, right? So that's the answer to the power question. They run great in terms of voltage. They run great on between kind of 2 volts and 5, 6 volts. You can't run them as fast at lower voltages, and where these cutoffs go depends chip to chip. But all of them run stably at 1 megahertz at, down as low as 3 volts, and some of them as low as 1.7 volts. So if you really want to reduce your power requirement, the first way to go is you knock the voltage you're running it on down and you increase your battery capacity. They run great on rechargeables, et cetera, et cetera. Let's see, other questions. Video tutorials or podcasts? I would love to. In-depth, I would say the Bruce Land's Cornell AVR class is really in-depth. That's really a super resource. In terms of just, that's where I would go if you wanted it serious and in-depth in video form. You can look up Bruce Land on YouTube and you'll find him, no problem. Anyone else have any other questions?
Hi there, Elliot. We do have a few more questions that have come in. Is your refresh button red, perhaps?
Oh man, I didn't. Thank you. I'm sorry. There were a bunch more questions. I didn't see them. My apologies.
You.
Okay, I see the rest of the questions. Thank you very much. So one question is, what are the best in-circuit debuggers to use on AVR to see registers and memory? That's a tough question. In terms of simulators, AVR or Atmel's AVR Studio has a really nice one step at a time debugger where you can see what's going on in simulator and debugger where you can see what's going on in everything. It's not in circuit. So it's a simulation. So if your problem's coming because you have an analog value that goes too high because it's hooked up to something and the light gets too bright, you'll never be able to debug that using a simulator. That's where I like printf style debugging. I just send the data across the serial line and read it out. On the other hand, there are in-circuit debuggers, and the Mega series chips, I'm not sure if it starts with the 88 or the 168, but above a certain size, they all are able to, you can use JTAG and in-circuit debuggers for them. I've honestly never played around with that. I know the capabilities there to use JTAG on some of the high-end chips, and I'm pretty sure that AVR Studio does it, but really don't hold me to the fire on that. Yeah, I haven't done that as much as I probably should have. Next question. Any popular discussion forums for AVR? Oh, man. Every other project on Hackaday has AVR stuff. The most popular discussion forum, I would say, and probably the longest running and most knowledgeable, is AVR Freaks, which is actually Atmel's, the manufacturer's forum. It's actually really pretty good resource. If you're able to speak German, or there's good English content on it as well, is also microcontroller.net. You'll be able to find that. Is really very strong. A lot of the GCC developers are actually German, it turns out, and post actively to microcontroller.net. But for the strictly English-speaking world, I would have to say AVR Freaks, Atmel's, is a very good discussion board. Let's see, there was a question about the timer mode. Yeah, PWM 10-bit mode, 11-bit mode means you can use that resolution. So the question is PWM 10-bit mode means that you have 10 bits to count the timer for the intervals, and the answer is yes. There are 3 timers. Two of them on most of the chips are 8-bit. One of them is a 16-bit timer. The 16-bit timer you can down rate, so you can use it as an 8-bit timer or a 12-bit timer or a 16-bit timer or anything in between, depending on what resolution you want out of it. And that's right. It means you have that many bits to count the timer for the interval. I didn't get into it. There's a prescaler for the timer, so if you want things to run really slow, you can first divide the internal clock by up to, I think, 1024, and then count off of those bits. So you can get the timer to cycle around kind of once a second almost, if you're down to about once a second. If you want to do that. And you have pretty good control of the resolution with the 16-bit timer. The 8-bit timers are just stuck on 8. But you can set what the maximum value is there. So you can change the frequency fairly easily. You'll have to look at the data sheet. Question, will interrupt routines nest or must they be managed individually? The default in AVR GCC is to have them not nest. That is, the default is not to interrupt an interrupt routine. So if 2 interrupts fire at once, it runs the routine with the highest priority, and then once it's done with that, it drops back to your main program, notices that it still hasn't handled the second interrupt, and then it handles that one, and then goes back to your main program again. So there is a kind of an implicit priority scheme there. One of the important things if you're getting serious about interrupts is to write very short interrupt routines, because if you write them long enough that you get other interrupts piling up while you're still handling the first, you can get stuck and your main program will never have time to run again. So keep your interrupt routines short. I've seen comical and terrifying things happen with robots that run on long interrupts and get caught in loops where they end up chasing people around the room. Amusing but dangerous. Keep your interrupt routines short unless you really know what you're doing. There is a flag where you can allow interruptible interrupts, and this, you really have to know what you're doing if you're going to do that. Make sure you need it. But you can do essentially everything is the short answer. The long answer is you could do everything. The short answer is keep your interrupts short. Jeff asks, can an old STK 500 be the programmer? Yeah, they're awesome. They're one of the first programmer setups. The problem with an STK500 is it's a serial programmer, and you need a serial port on your computer to talk to it, or you need a USB to serial converter. Parenthetically, a lot of the modern USB programmers either emulate the STK500 or this other programmer family, like actually the ISP, like the Arduino. The one I told you guys to flash into the Arduino is a STK500 protocol compatible hardware programmer. So the STK500 is by far not dead. It's just that nobody has serial ports on their computers these days. If you've got one, by all means use it. I'll refresh the questions one or two more times, and we'll see what we do. Are there any other microcontrollers besides the Arduino that are worth using? Oh my God, the answer is yes. There's a million. I won't even pick them. The PIC series, there's a bunch of 32-bit microcontrollers now. Some of the ARM chips. There's tons and tons and tons. The good news is that all of them are programmable in C. So anything you spend learning here, trying to program AVRs in C, you'll be able to translate over to programming ST's ARM chips in C or whatever. You'll have to learn new peripherals, but not even really. They still have timers. They have 32-bit timers instead of 8-bit timers. But it doesn't really change anything about the fundamental way you approach programming for the chips. It'll change some of the code, but not anything serious. Let's see. I'll do a couple more, and then we'll bail out. One question is on printf and string functions. That's a great question. The answer is that printf and string functions work very well, but take up a lot of memory. So if you're using one of these chips that has 8K and you take up 1.5K for printf, you may not want to do that. There are two versions of printf, actually. There's one version that does do floating point and another that doesn't.
Please stand by while I reconnect the speaker line. And pardon me, we now have Mr. Williams reconnected.
Hey, yeah. So the question was printf libraries, do they work? And the answer is yes, they take up a lot of space. If you're using a small device and you're memory constrained, you're better writing your own routine for it. For instance, if you just want to send strings across the serial port, that's like, maybe 10 bytes to write that routine. If you really need all the bells and whistles of printf and you have a K to spare, by all means do it. The floating point version of printf takes up even more memory space because it has to load the floating point memory library, which isn't normally used. And so if you're on one of these chips that has only 4K of program memory and you're using half of the memory up just to print out the number 2.3, you're misallocating things. On the other hand, they do work, and if you've got a 16K microcontroller and you're using 8K of it, by all means use printf and make your life easier. I don't very often. It's actually easy enough to print out strings that I don't even bother with it. But there have been some times when I do. So another tool in your arsenal. It's actually almost all of the standard C libraries available. Some of the file I/O stuff isn't, although some of that is written for SD cards and fills in, which, let's see, one more question maybe, or two. Here's another question, actually it's super interesting. Dave N. writes, is there enough hardware speed space to do touch tone decoding, or is this something best left to an external chip? I've tried to do this actually in the context of receiving two-tone radio signals, so receiving like old-style modem data, old-style two-pitch modem data over radio. And the answer is yes, it's totally possible if you have a really clean signal going in. Frequency detection stuff, on the other hand, is hard when it's really noisy and you get lots of spurious zero crossings, et cetera, et cetera. I honestly find it's hardest just algorithmically, and in that sense it's best left to an external chip or something. That said, I've done it and a bunch of people have. There's an amateur radio group doing there's amateur radio groups doing work on this sort of things, and I'm sure you can find code that's specific for that. There's a specific Gertzel algorithm that you can run on the AVR that actually works pretty well as long as the signal's not really noisy. I hope that's not too technical, but there you go. And maybe the last question I'll take is, have you ever used AVR libc? Does it have a small memory footprint? I think so. The trick is that if you set the compiler options right, you'll only use the functions that you use. And so in that sense, you can have as small a memory footprint as you'd like. On the other hand, as I said before, things like printf can be real beasts. There's also some confusion in AVR land. There's another library called AVR lib, which is really interesting and fills in some of the kind of embedded specific library things that you might be interested in. It's got a nice buffering system to do serial input and output, which, to be totally fair, the Arduino has a really nice buffering system to do serial input and output. If you wanted to steal one for that, you might do well to borrow the Arduino one. It's written in C. What else? You'll find if you look that there is tons of code examples out there. And so there's something for everything. These days there are people who are really concerned about packing as much code into as small a space as they can. There's also the contravailing factor that the chips are becoming so cheap that it's just easiest to buy a 16K chip and not worry about it. And that's kind of the tack that Arduino is taking these days. I mean, their standard chips now have 32K on them. And so all of the memory worries that you had before don't really matter as much. There's still the performance and speed issues, but code space isn't as much of a problem anymore as it used to be 10 years ago, 15 years ago. So I tend not to sweat that stuff anymore. And I'm going to hit refresh one more time, and if there's no more questions, I will say thank you very much, everyone, for attending.
Great. And with that, folks, we're going to say a very big thank you to you, Elliot. That was an incredible webcast you presented today. So much great information, and we thank you for spending time with us and for sharing all your knowledge and expertise.
Thank you very much. My pleasure.
folks that attended our webcast today. We thank you for attending and hope you benefited from it. And as we close out, we would like to let you all know that we pushed out some URLs and some discount codes to you. Elliot has a great book. It's right there on the screen, AVR Programming from Maker Media. So much good information in that book. If you like what Elliot talked to you about today and showed you, there is so much more in that book that can really help you with your project. So we definitely encourage you to take advantage of that discount. You can get the ebook today for 50% off. Again, we thank you, Elliot. We thank everyone for attending, and a big thank you to Gretchen for helping out with the group chat there. We appreciate seeing you at the event and for your participation. This will conclude today's webcast. Goodbye, everybody.